Hello, welcome to today's video on numerical methods for differential equations, although the content we're covering in this video requires a different approach to the previous iteration approach we were using on the previous content in this chapter. And therefore it's also worth noting we're not going to be introducing any new iteration formulas in this video. Instead, we're going to be making use of ones we've hopefully already come across before. So as a reminder, I'm expecting you to already know about the midpoint method formula and also the formula for solving second order differential equations that we've used before. As a reminder, also, luckily, although these things aren't in the form booklet, these are two formulas you don't need to know off by heart, as they should usually be given to you in the question. And that is actually all the preamble I'm going to give you, because the whole point of this stuff today is that it's stuff that's only applying things we've already seen before, but in a bit of a different scenario. So let's show that by taking a look at an example. The thing to be aware of with these questions is there's several clues about them that make you aware that they're different to the types of questions you've been dealing with normally, which is important so that you can spot that you need to take this different approach. Some of these clues are quite subtle, but hopefully there's enough of them appearing in a given question for you to be able to spot that it's one of these different questions. For instance, for a start, if we take a look at our second order differential equation, you'll notice that it involves a dy dx. And you see, that's unusual because in the previous questions we were dealing with, that didn't appear. However, it's worth pointing out that this isn't a necessary condition for one of these questions, so this will only appear sometimes. The reason this is weird is it means we don't have an accurate way of calculating dy dx for any future iterations, which introduces more inaccuracy if we're just doing the usual iteration method that we were doing before. The other strange thing is what happens when we look at the x values, because we've been given a starting point of x equals 2, and we want to find the y value when x is equal to 2.1. But as the step length is only 0.1, that means we're only being expected to do one iteration. That's odd because normally when we solve second order differential equations using numerical methods, we do the first iteration using Euler's method, and all the future iterations is only when we start to use the second order derivative method. But the problem is if we're only doing one iteration, then we're never actually going to get onto using the second order derivative method, which seems a bit weird considering it's a second order differential equation. The final but most important clue of all, though, comes when you look at the iteration formulas the question's asking us to use. They've given us the second order derivative formula, which kind of makes sense considering what sort of differential equation we have, but then seems weird when compared with that one iteration issue we've already pointed out. But the other weird thing is the fact they've given us the midpoint method, which is strange because, as we've already pointed out, normally you use one iteration of Euler's method before you use the second order derivative method, not the midpoint method. So all these clues together are leading to us to realise it's not one of the usual questions. But therefore, how do we approach it? Let's take a look. Splitting the page in half so we've got more room to do stuff, the first thing to point out is that we have effectively been given in the question x0, y0, so that's x0 is 2, y0 is 9, but also interestingly we've also been given dy dx 0 because that's the value of dy dx at that x and y coordinate. The reason that's interesting is because it means if we want to be able to use the midpoint method formula, then that means that our n has to be 0. So therefore it means we're using the formula dy dx 0 is equal to y1 minus y minus 1 all divided by 2h. So therefore for this scenario that would be leading to us having the formula y1 minus y minus 1, both things we don't have because we've got y0, divided by 2h would be 2 times by 0.1, so 0.2, equals our dy dx value of 4, leading to the equation y1 minus y minus 1 equals 0.8. A bit worrying because we've got two unknowns, and that is only going to get more weird because then we could also go, okay, we've got x0, y0 and dy dx 0, so we could calculate d2y over dx squared 0 as well by plugging in the relevant information into the original differential equation at the top. So that'll be x cubed, so that'll be 2 cubed, plus 2 lots of y, so that's 2 lots of 9, lots of dy dx, so that's 4. And if you work that out, you're going to get 72 plus 8, which is 80. But therefore, we also compare that information to the iteration formula and realize that again, we need n to be 0 in order to be able to plug this information into that iteration formula. So therefore, we're using d2y over dx squared 0 is equal to y1 minus 2y0 plus y minus 1, all divided by h squared. Meaning we have 80 equals y1 minus 2 lots of y0, which would be 18, plus y minus 1, which again we don't have, all divided by h squared, so that's 0.1 all squared. Again, a bit weird because we've got two unknowns in that formula as well. But that's where the magic happens, because what this is going to mean we have is two equations with two unknowns, and what do you know? It's therefore simultaneous equations. And that's why this is only a one iteration question, because you have to do not iterations per se, but solving equations to get the value you want. Interestingly, although we could find both y1 and y minus 1, we don't actually have to find them both. We only have to find the value of y1 because that's the y value when x is equal to 2.1. That's the thing we're interested in finding according to the question, and the other thing is actually irrelevant. It's almost like the pretend iteration before our starting point, which is a bit weird to think of, but therefore that's why we aren't interested in actually finding it. So let's get on and do that. We could rearrange this second equation that we created by multiplying both sides by 0.1 squared and also then adding 18 to both sides. So therefore that will get us 18.8 is equal to y1 plus y minus 1. Cool. And therefore now we've got two simultaneous equations, and actually they're going to be very easy ones to solve. Normally I'm very much encouraging students to always do the substitution method, but because of the way these equations are always created, the classic elimination method is actually always going to work in these sort of questions. So for instance, I can just add these two equations together and it will mean the y minus 1s will cancel out. Therefore meaning when I add the two equations here and here together, we end up with 2y1 is equal to 18.8 plus 0.8, which is of course getting us 19.6. And therefore that means y1 is just going to be 19.6 divided by 2, which is of course going to be 9.8. And therefore the final answer is, at x equals 2.1, we can say that y is approximately 9.8. Cool. That's all there is to it, and actually that'll do us for today's video. Hopefully you found it useful, and I hope you don't get caught out by these questions, because at first they look so similar to the other types of ones we've been dealing with so far, until you look at those more subtle clues. See you in the next video. Goodbye.